Dewpoint depression. So what is the dewpoint depression? It's simply the difference between the air temperature and the dewpoint temperature. So if you like, on an aerological diagram as shown on the right, it's the distance between the two lines. And if we examine this trace for 23 UTC on the 1st of March 2006, you'll see how the dewpoint and the temperature profile sometimes come close together, and at other times there's a very large distance. In other words, there's a large dewpoint depression. And so what we can do with the dewpoint depression is use it as a proxy for relative humidity and the potential presence for stratiform cloud. Stratiform cloud is layer cloud where there are no or the very weak convective motions within the cloud. It's layer or streaky cloud. As a first exercise, consider the following trace from 997 hectopascals to 600 hectopascals. Plot the trace on a skew T log P aerological diagram, and then calculate the dewpoint depression at the surface 925, 850, 700 and 600 hectopascals. Assess where there is cloud likely and what sort of cloud it is, and then work out the cloud base and top using the ICAO scale provided on the left hand side of the diagram. Stop the video now and plot this trace, discuss it with your colleagues, and then start the video again. So what did you find? Here's the actual trace in red for the day, and you'll see that there's a small dewpoint depression in the lower part of the troposphere. The calculated values you should have come up with would have been 1 degree for the surface, 1.7 at 925, 1.3 at 850, and then they come sharply apart above that. So nearly 9 degrees at 700 and 15 degrees at 600 hectopascals. And if you go and look at the values of R and RS for each of those levels, you'll see high humidities in the lower parts of the trace to 850, and then dropping back to nearly 50% and 30% at 600 hectopascals. So it looks like there's a clearly defined region where the atmosphere is very moist, and we can infer stratus cloud. So stratus cloud is stratiform cloud that forms near the surface, and within certain tolerances you can see the base is about 300 to 500 feet and the top at about 8,000 feet. So that's pretty thick stratus cloud for this particular environment. We can back that up. Again, there's the trace at the bottom showing the deep moist layer. The top left hand figure is a webcam, and it shows that there's precipitation occurring and that it's very cloudy. The middle figure is a relative humidity field at screen level, and you can see over the large Melbourne area values are at least 70% or above, up to 96%. Finally, on the right hand side is a mean sea level pressure chart. What you can see, there's a complex low on the east coast of Australia, and what's been marked in with the arrows is trajectories. So the idea is that warm, moist tropical air is being advected from the Coral Sea all the way down, wrapped around that low, and advected over Melbourne in that southerly airstream that you can see in the sonde. So normally you wouldn't expect a southerly airstream over Melbourne to be quite that humid, but in this particular case, because there's that advection of the warm, moist tropical air mass, that results in this very humid or near saturated air mass producing the low-level stratus. So we can use relative humidity, which you can again infer from this dewpoint depression, but how much is enough for cloud to form? What you've seen from the previous slides is that there was low-level stratus, but the relative humidity was less than 100%. So normally we'd expect saturation to occur at 100%, but we see in fact that saturation occurs at relative humidity is less than 100%. Now firstly, there's the whole issue of dirty air, or what we call cloud condensation nuclei, and the particles in the air that make it easy to form cloud, and you'll discuss that in a cloud microphysics course. Secondly, there's the whole issue of what happens below 0 degrees Celsius. And remember, there's a difference between the frost point and the dew point. The frost point is where you have saturation with respect to the water vapor over a plain ice surface, and the dew point is saturation of water vapor with respect to a plain surface of liquid water. below 0 degrees Celsius, the frost point is higher than the dew point, which means that even without 100% relative humidity, you'll be getting the formation of ice crystals in the cloud. There are also inaccuracies in radio sonde instruments once they become wet or frozen, so that can cause all sorts of problems in the sonde. And finally, water vapour isn't necessarily uniform. It can often be patchy and vary in space and in time. So you may not always be sampling the air mass that you're actually seeing on average that produces the cloud. So what we do then is consider the possibility of cloud in a layer where the trace shows a dew point depression of less than about 5 degrees Celsius. And in particular, you want the dew point depression to be low and constant over a large layer, about 50 hectopascals or greater. And of course, finally, you never do any of this without consulting a satellite image as well. So you're trying to have a consistent picture from multiple sources of information. On the left-hand figure here, we have the frost point minus dew point as the blue line, going from 0 degrees all the way down to minus 50 degrees dew point. And the net result of that figure is to show that the frost point is always larger than the dew point, as we discussed before. If you look at the sonde now on the right-hand side, the SKU-T log P aerological diagram, you'll see there are some layers in that trace lower down where the dew point depression is small, and then above 25,000 feet, you'll see that the profiles slowly diverge. One of the things we know, and again you'll discuss later in cloud microphysics, is that at about minus 20 degrees Celsius, there's very efficient formation of ice crystals. And so, although you can see the temperature and the dew point temperature profiles diverge above that level, what's actually happening is ice crystals are forming. So the frost point temperature is larger than the dew point temperature. So don't be fooled by the fact that the profiles are diverging. You're getting ice cloud forming above that level. Again, here's a similar comment for a different sonde. The temperature and the dew point temperature profiles gradually diverge from each other at a temperature which is equal to dew point temperature, which is equal to the frost temperature of 0 degrees, even though the entire troposphere is saturated. Remember, we talked about pseudo adiabats on the SKU-T log P, so we ignore ice, only take into account supercooled water. And the sounding itself is only showing the dew point temperature and not the frost point temperature. So ice is explicitly ignored, and so we need to always remember that ice formation starts to occur above 0 degrees in the atmosphere, definitely forms efficiently in the region about minus 15 to minus 20. So whatever the profile's doing, if you think that there's a high-level ice cloud, then it's quite possible that there is, and you need to confirm that with a satellite image. Finally, thinking about diagnosing layer cloud from numerical weather prediction output, typically we'll use a relative humidity of greater than 75%. And you can see here there's a comparison on the left between a visual satellite image and a relative humidity field for 900 hectopascals on the right. Remember that models aren't perfect, and there will be spatial resolution issues and inaccuracy, which will at times produce relative humidity values that are going to be lower than the actual. Moisture is actually quite a tricky parameter to keep track of in a model and to accurately reproduce what's happening in the atmosphere. And values vary also in different numerical weather prediction models. So use 75% as a first guess when you're evaluating what a model's saying, and always ground truth the model with what's happening in the real atmosphere.